Yeah, multi-class classification. Okay, so what I did, just so you know, compared to last year, I had some stuff about ethics and fairness with neural networks and computer vision, and I moved those from this lecture to the ethics lecture. So you're going to get that later. And in its place, I added this because we keep kind of dancing around this issue, and I want to just address it finally. So let's address it. And this is, oh, I should say one other thing. Um, Okay, let me actually say one other high-level comment. So we are now in the second half of the course, and the format of the second half of the course is a bit different. So the first half of the course was fundamentals. How do I deal with categorical variables? How do I deal with scaling? How do I deal with pipelines, hyperparameter optimization? It was like the very fundamentals of tabular data. And by tabular, I mean something like this. You have your columns, which are your features, and your rows are examples. And so we had a kind of data set of the week. Every week, I think we had 4 or 5 data sets so far that allowed us to highlight different things. The second half of the course, which starts today, is kind of the common special cases. So for example, today we'll talk about if you have images as your input instead of features. And next time we'll talk about time series data and language data and all kinds of things like that. So we won't really have the data set of the week format anymore because we will be jumping around too quickly to use the same data set for the whole week. Like today we'll just talk about images and then be done with images. So basically the first half of the course was like the fundamentals for tabular data, meaning a table, like the most common format I expect you to see. And then here I'm just kind of building awareness of all the other things you might see and giving you the tools I think you might need to start to tackle those problems, but not going into as much depth. So that's what I want to say. So we don't have a data set of the week anymore. For this, talking about multi-class classification, that means classification where there are more than 2 classes. So all the classification we did was like, I like cilantro, I don't. I'm fraud or I'm not fraud. I'm high income or low income, etc., etc. And multi-class classification is simply when you have more than 2 categories. So this wine data set is just like a very not so exciting standard data set that's built into scikit-learn. And the point is that, so this is X, we have our features, we have our rows, and this is Y. So we now have 3 different classes here, 3 types of wine, I believe. And this happens all the time. And the reason why I want to start today with this is because the image stuff we're going to talk about is going to be a lot about multi-class classification as well. It doesn't have to be, but just the common examples happen to be. So I just want to say multi-class classification, you will likely encounter it. It is not that big of a deal most of the time. So all the stuff we talked about, random forest, fit, predict, it's all good. It all runs, and you don't need to think about things differently than we've been thinking about them so far. You could still get a feature importance, just like we had before for the random forest. But just the thing I want to pay attention to for us is the linear classifier, the logistic regression, because there will be some differences here. There's also some differences in how you would interpret something like a SHAP plot, which I didn't put into the lecture today, but maybe I should have. The question in the chat, what does the target values represent? I believe there are 3 types of wine, and you're trying to classify what type of wine it is based on these components in the wine. Yeah. So the logistic regression is the one case where we need to be a little more careful when we move from 2 classes to multi-classes. It's actually rather confusing. So we can have our logistic regression, we can predict, and it works, and we can predict proba. And here's now one difference from what we had before is we have 3 columns instead of 2, but that makes sense. I mean, before we had it's the probability score of this class or this class, and now we have 3 classes, so we have 3 scores, and they still add up to 1, and so that's all good. So we had 2 columns before with 2 classes. With 3 classes, we have 3 columns. If we had 10 classes, we'd have 10 columns. And so that whole thing of thresholding at 0.5 doesn't really apply anymore. Instead, the way predict works here is it takes the biggest of the three, because you might have something like 40%, 30%, 30%. And so none of them is bigger than 0.5, but you still need to make a prediction, so you're going to pick the 40%. And so that's how it works here. And if we look at the argmax, which basically tells us the index of the max, then it's saying 2, meaning, why does that look? Oh, because I have to rerun it. Right, so the biggest one here is number 1. That's why we have a 1. The biggest one here is 0. See, this is 99.9%. So it picks this one. The biggest of these three is this one, that's 98%, so on and so forth. But you can see this one is actually, what is that? So confusing. 1% and 20% and 79% or something like that. Yeah, I might have messed it up, but you get the idea. So that the biggest of these three is the 77%, and so it picks that one as predict. Okay, so that's that. I'm just showing you that the predictions are the same as this. So that's what predict is doing. It's taking the biggest probability. But now the weird part. This is why I wanted to talk about this specifically. Before predict proba had the number of columns was equal to the number of classes. 2 classes, 2 columns, 3 classes, 3 columns. The funky thing that you just need to watch out for is that before, with 2 classes, we had 1 coefficient per feature. And now with 3 classes, we have 3 coefficients per feature. And that's this kind of discontinuity that tends to be very confusing. And so here are the coefficients. So here's the deal. Now we have 1 coefficient, here's the coefficient, per feature per class. And before, so when we had 2 classes, we only had 1 coefficient per feature, and basically it told us like which direction. But there is a way to implement logistic regression such that when you have 3 classes, you only have 2 coefficients per feature. But it is customary to kind of make this discontinuous jump that with binary classification, you have 1 coefficient per feature. And with multi-class classification with k classes, you have k coefficients per feature, even though the binary case is not really a special case of that anymore, because binary is 2 classes, but we don't have 2 coefficients. So this is super confusing. And I'm not really going to go into the math of it, but I guess I'm just going to say that you only really need 2 coefficients to kind of express everything here, but it is customary to have 3. And interestingly, what scikit-learn is doing here is it's actually making the coefficients add up to 0 for each feature. So if I sum these rows here, you can see the sum is basically 0, 10 to the negative 12, 10 to the negative 13. And so it's kind of like saying, well, for 3 classes, we have 2 coefficients, but then I'm going to add another coefficient such that they all add up to 0. This is a bit of a rabbit hole, and I don't want to go all the way down this rabbit hole, but I just want to bring to your attention that you're going to see this, and then the interpretation is a little more confusing here. I would still interpret like this coefficient here as if you increase the alcohol, you're going to be more likely to predict class 2. And if the coefficient is negative here and you increase this feature, you're going to be less likely to predict class 1. But all the interpretation gets a bit muddled here because you actually have these 3 probabilities. And so as you change one of these features, it's really those 3 probabilities that are changing. And if I could just point out a kind of symmetry that you have these 3 probabilities, 1 for each class from predict proba, that need to add up to 1 because they're probability scores. And we kind of have something analogous going on here, that we have these 3 coefficients, but one of them's kind of redundant because each coefficient is kind of leading us towards a probability for that class. And since the probabilities have to add up to 1, and so one of the columns is redundant, one of the columns here is kind of redundant as well. Okay, let me take some questions in the chat here. Okay, so one person was asking about linear above. So that's a terminology issue. I refer to logistic regression as a linear classifier because it is a classifier and it is linear, like in the sense of that it has these coefficients that get multiplied by the features, just like linear regression. So yeah, logistic regression can be referred to as a linear classifier. What are the 1, 2, and 3 referencing here? I think maybe this is asking about the 0, 1, and 2, but those are the 3 different classes in this 3-class classification problem. So there's 3 types of wine. Now there's a question about this. Yeah, so now this is where it gets, so someone was saying, wait, for alcohol, shouldn't a higher value mean class 0? Yeah, so this is now getting to be where it gets tricky. So if you increase the amount of alcohol, the class 0 has the highest coefficient, so the probability for class 0 will definitely go up. But I think, although I'll double check this, I think that the probability for class 2 will also go up a little bit, and the probability for class 1 will go down. But now I feel like I should double check and confirm that. But I think that's the interpretation here. Can we think of this as 3 separate logistic regression models, one for each category of the output variable? Excellent question. I will get to that in a minute. Yeah, just a minute. Okay. There are times when we face target values to be numeric and categorical. Can we predict 2 different types of targets with one algorithm? Yeah, we can, and maybe we'll talk about that a bit later with neural networks, but that's kind of fancy. Isn't logistic using a sigmoid function, so it's not linear? Yeah, so we call it linear because the thing that you get right before you stick it into the sigmoid function is linear. And so we call it linear, or the statisticians would call it a generalized linear model. So the word linear still comes in there. I would call it a linear classifier personally. Okay, yeah, so yes, this is the thing where, let me scroll up. Oh, I didn't put that in. Okay, let me show you this. Okay, so see what's complicated here and makes our life more complicated is that there's actually a parameter here called multi-class. Again, with random forests, all those other things, you don't have to worry about this. This is just very specific to logistic regression, but the reason I'm going into it is logistic regression is really popular. So I want to talk about it. So if we go down to the documentation, multi-class. So see, there's actually two different things scikit-learn does. OVR, which stands for one verse rest. And that is the question that was in the chat earlier. That one is 3 separate classifiers, one for each class. However, there's also multinomial, which is one big logistic regression that kind of mixes them in a more complicated way. And then there's auto, which selects between them kind of automatically, but for our purposes, it defaults to multinomial. So I wouldn't worry about this too much, but at the very least, I want you to know that the interpretation of the coefficients for logistic regression specifically is confusing when you get to multi-class classification. And that actually reminds me, ooh, this is way too long. Sorry, I did not know whether to go up or down there. Should have gone up. Okay. Okay, so yeah, the coefficients sum to 0. I don't really want to go into that right now. I just want to keep going. And so, yeah, we have these coefficients. We talked about that. Oh, and then we had this here. We talked about all this. So yeah, we go into this more in 340, but I don't really want to go into it here. In terms of getting a general feature importance, so when we had just one coefficient per feature, then we got the feature importance by looking at the absolute value of that coefficient. So if the coefficient was huge, then that feature was important regardless of whether the coefficient was positive or negative. Here we now have all these coefficients per feature. And so I looked inside the source code of scikit-learn, and the way it distills it down to a single feature importance is it takes the sum of the squares of the coefficients, which should mean that if one of the coefficients is very large, it's going to be considered a more important feature. And if they're all kind of about the same, then it should be considered a less important feature. So I don't want to go into the details of that either, but the reason why we care about this is if you remember, if you've already watched the screencast from lecture 12 with feature selection, we really want a single number representing feature importance for every feature. And so we need a way to get from these three coefficients to a single number representing feature importance. Okay. I think this is basically it. Right, so confusion matrix. So we talked about confusion matrix in lecture, I don't remember what it was, 6 or 7 or 8. And so I just want to point out, you can make a confusion matrix for multi-class classification. Now you have 3 possible true labels and 3 possible predicted labels. The diagonals mean you're getting it right. And all the off diagonals are the different types of mistake you could make. It was actually 1 and you predicted 0. It was actually 0 and you predicted 2, etc., etc. And so we don't have exactly precision and recall in the same way. If you wanted precision and recall, you would have to pick one of the classes as your like special positive class. So when you actually call this classification report in scikit-learn, it's like, well, if the special class is 0, and if it's 1, and if it's 2, but I think this is kind of getting, a bit beyond where we need to go in this class. The last thing I want to show is just these decision boundaries. So we looked at these plots earlier. I apologize for the colors being messed up, but here's our training data. I'm just subsetting 2 features because there's actually like 12 features. I can't make a 2-dimensional picture with 12 features, but just taking 2 features to make a plot. Here's kind of what a logistic regression is doing. It's kind of cutting the space into 3 with these straight cuts. And so all the stuff over here gets this prediction, all the stuff over here gets this prediction, all the stuff over here gets that prediction. And here's what it looks like for random forest. Again, just looking at 2 features. And so yeah, the point is you have 3 different kind of shades of possible predictions because you have 3 different classes. And here, well, here is an SVM, which is not a classifier we've actually talked about in the course, but you get a different kind of blob, which is kind of fun to look at. Okay, so that was that. Let me look in the chat for more questions, and then we'll get back to it. Okay, I think we basically talked about that. Okay, that sounds all good. Would we do feature selection to account for the overall model? Yeah, we would. Typically. I mean, you could get a feature importance for the different classes, but we would normally include it overall. What is positive here? So there is no positive here. We have 3 classes, and they're called 0, 1, or 2, but they could be called anything. Why not just make 3 separate models to predict for each class? Okay, so that's a great question. The reason we don't just make 3 separate models to predict for each class is because then they can't share information with each other. And so, for example, imagine that you only had like 50 training examples for one of the classes, and then you just made a separate model for that. It wouldn't get to learn from, okay, it's hard to explain this in a understandable way. If you train one big model, it should technically have should technically be a little bit better to do everything at once. However, training 3 separate models is not insane, which is why it's one of the possibilities in scikit-learn when you set multi-class equals OVR. That is training 3 separate models. So I'll say it's not insane, but it's you can do it. But for other things like random forests and stuff, decision trees, you don't need to worry about this at all. You can just have one big tree and it gracefully handles multi-classes with no problems. Okay, last question before moving on. Does the biggest, most positive coefficient for a feature mean we are most likely to predict the corresponding class? No, so it means that if you increase that feature, then it will push things towards the corresponding class most. But we can't really make a general statement about what class we're most likely to predict in general because it depends what the features are going to be. I mean, there is this intercept thing that I very briefly mentioned, but we don't really talk about in this course. That's kind of like an overall, how likely are you to predict each class? And so I guess it seems to be favoring class 1 here, but I don't really want to go into that. For multi-class, could we just optimize that hyperparameter and see which one does better? Yeah, sure, you can. That's the attitude I'd like to see. I don't think it'll make a huge difference, to be honest. Okay, moving on. Intro to computer vision. So, computer vision is a term that refers to understanding images and videos. These days, usually using machine learning or AI. There's kind of traditional computer vision, which is out of fashion now because machine learning has taken over the field more or less. Computer vision has many kinds of tasks that could be of interest. So the one I'm going to talk about today is image classification. So given an image, what is it? Is it a cat or a dog? And often these are multi-class classification problems, which is why I just introduced multi-class classification. We'll be talking about some multi-class image classification later today. Is it a this or this or this? But there's many other tasks you can do, like object localization, like finding faces in images or finding people. There's image segmentation, so cutting an image into the different parts. Motion detection. So once you get into video, there's whole other things. And so as you can imagine, these problems are of very high interest for, self-driving cars, for surveillance, for military, for random apps on your phone, for your camera. So yeah, for compression. So this is just like super buzzing area of machine learning that we will not really do justice to, but we will at least I'll give you some suggestions today. So as of, say, like 5 years ago, computer vision is just completely dominated by not just machine learning, but by a particular type of machine learning called deep learning, which is basically a synonym for neural networks. And so that's why I want to talk about neural networks. And maybe it's a bit more than 5 years now. Time is passing. Around 2012 was the inflection point, I would say, of this stuff. So I'm going to only describe neural networks in an extremely high level way to you, which is to say a neural network is kind of like a pipeline. That's how I want you to think about it. So remember what our pipelines did in scikit-learn is you could have a transformation and then another transformation, then another transformation, then another transformation, however many you wanted. We never had more than 2. And then some kind of classifier or regressor at the very end. This is how I want you to think of neural networks. And you'll see by the end of today why it's useful to think about it that way. I'm going to show you some code. As you can see at the very top, I imported TensorFlow, and TensorFlow is part of the course environment, so you should all have it installed. So this code here is TensorFlow code, and it's actually a part of TensorFlow called Keras. I'll get to that in a minute. But what happens here is, so this is a kind of code you can write for neural networks. And this is not necessarily going to make sense, and that's fine. But what I want to at least show at a very high level is that you keep adding more steps. And these are basically your transformations in the pipeline. And that's why we're writing the code like this. So in scikit-learn, when we specify a model, we just do it in one line, like random forest, and then we put in some hyperparameters. But here, the way that the TensorFlow and Keras is designed is that you actually use multiple lines of Python code to just do this, to just set it up. So what used to be this one line of Python code in scikit-learn is now multiple lines of TensorFlow Keras. Because in a way, I want you to think about it as you're layering on these transformations into your pipeline. And then this last thing is your, in this case, linear regression, or your ridge, basically, coming on at the very end. So transformation 1, transformation 2, linear regression. And what's interesting is that when we do our transformations earlier in this course, like what happens to the number of features? Well, scaling keeps the number of features the same, but one-hot encoding actually changes the number of features that you might have. And so what these numbers are in the neural network is you're basically saying how many columns should the data set have after this transformation. And so in this case, I'm actually making a neural network that operates on data with only one column, transforms it to have 10 columns, transforms it to have 15 columns, and then gives you a single number at the end, which is your prediction. And so I know this is like super high level and vague, but this is the level of detail we have time for. Plenty more detail on this in CPSC 340 about how it works, but I'm going to get you some actionable useful information by the end of today that you can start applying this. So yeah, we talked about that, talked about that, talked about that. I'm not even going to touch this. Just some extra code with TensorFlow. Okay, so here's some random data that I made. This is a regression problem. There's one feature. Here's your one feature X. This is your target value Y that you're trying to predict. And all I'm really going to show you is that we can call .fit, just like we're used to calling .fit in scikit-learn, and it's going to fit this neural network that I specified above. And I can show you, this is like the regression curve. So we could have done this too. I actually didn't show you this kind of pictures for like a random forest or, well, for linear regression, it would just be a line. But the point is it can fit data. And okay, that's probably not super shocking to you. And then in TensorFlow, the thing is called evaluate instead of score, but basically everything is more or less the same as what we're used to. Okay, let me pause for a minute for questions in the chat. So is it true that Google's CAPTCHA system helps with image classification? So there used to be reCAPTCHA that did help with it. So reCAPTCHA was like also a crowdsourcing thing, and part of it was for you to verify that you were a human, and part of it was actually to label data sets. I don't know if that's still happening anymore. Can we have some homework with vision? I am not planning on that, but maybe by the end of today, you'll have some tools to play around with it on your own. Is the number of columns kind of like max depth in a sense? No, it's not. I don't really have a good analogy for it, except to say what I said before, that when you use one-hot encoding, you change the number of columns. And so at a high level, it is possible that a transformation will change the number of columns. And that's all I can really say about it. To clarify, TensorFlow is using the estimators of scikit-learn. No, it's not. So TensorFlow is a completely different package. TensorFlow is not built on top of scikit-learn. It's just its own thing. And it's mainly used for deep learning / neural networks. Why is the score so low? Oh, right, sorry. It's because it's reporting an error rather than R squared. So I think this is mean squared error or something like that. And that's why the score is low. How is tanh turning one column into 10? So I'm not going to go into that in this course. It actually doesn't have anything to do with the tanh. It has to do with matrix multiplication, but we're not going to go into that. it wouldn't make sense to spend time on it because not everyone has the prereqs. Okay, so terminology. So yeah, deep learning and neural networks are kind of the same thing, also called neural nets. What's all the craze about this? They can learn very complex functions. So in terms of the fundamental trade-off, they can overfit even very complicated data. Having said that, so can random forests. But the kind of killer app of neural nets, in my opinion, is for structured data. So for example, language or time series or images or videos, these are not tabular data like we had before with just a bunch of independent features. These are structured data. And we'll talk about that a bit more today. But yeah, this is kind of the killer app of neural networks. So they work amazingly well on some of these problems, but they have a lot of drawbacks. They often require a lot of data. They often require a lot of compute time, as you'll see later today. And often their compute time is so long, there's basically no point trying it on a CPU like we all have in our laptops. And GPUs is this other type of hardware that was originally made for computer graphics and now is used quite a lot in deep learning. So you have to invest in that. And often in the field, like Google will publish some result and everyone will be like, okay, well, that's not useful to me because I don't have like $800,000 worth of GPUs that I can use. So yeah, that's a problem. Large numbers of hyperparameters, a lot of hyperparameters, way more hyperparameters than we've ever seen in anything else in this course. And so hyperparameter tuning is extremely painful because it's slow every time and there's so many hyperparameters to try. They're not particularly interpretable. It's hard to get like good feature importances out of them, although I'll try to talk a bit more about that in a few weeks. And then there's some other stuff that when you call fit, it's not actually guaranteed to work. And we're not really used to that. We're used to, we call fit and it does its job. But with neural networks, for reasons we're not really going to go into this course, you're never actually really sure if fit did its job properly. And you kind of just have to hope for the best. And so that's another weakness. So yeah, I guess here's my pun of the day. I don't recommend training them without further training. Meaning I don't recommend you call fit on neural networks because it's actually hard. And so what I'm going to get to later today is I'm going to show you that some other people have called fit and then posted their thing online and you can actually take it and use it. Yeah, so that's kind of the plan for the rest of today. Deep learning software. So scikit-learn does have some stuff in it, but it's not really the real deal. So typically one would want to use TensorFlow or PyTorch if one was serious about this kind of stuff. PyTorch seems to be the preferred tool of choice these days based on my conversations with people who do a lot of this stuff. People seem to like PyTorch better. It's newer. Yeah, but I'm using TensorFlow for the moment for this lecture. And yeah, well, yes, the reason why my demo is in TensorFlow is because I made this demo 4 years ago and PyTorch didn't exist yet. So there you go. Okay, let me look at the chat and then we'll take the break. So scrolling up. Oh, there's a lot of activity in the chat. That's cool. Let's see. Yeah, people talking about buying GPUs. For those reading the chat, yeah, so NVIDIA is the company that makes a lot of these GPUs. How complex does a neural net have to be before we start calling it a person? Good question. Excuse me. I don't really know. But hey, we have an ethics lecture coming up and we can talk about some of that stuff too. Which one is easier to use, TensorFlow or PyTorch? I don't really know. I mean, TensorFlow might be slightly easier for like an absolute beginner, but people seem to be liking PyTorch better overall. If we have only tabular data, which one do you suggest we use? Great question. My recommendation to you is if you only have tabular data, don't use neural networks. I'm giving you lots of stuff in this course that tends to work really well, like all this light GBM and stuff. I wouldn't get yourself into this big mess known as deep learning and neural networks unless you have to. And probably the main reason why you would have to is if you don't have tabular data, if you have images or something like that. Otherwise, it's just too much hassle and not worth your while. That's my opinion. Because I went through the list of hassles and they are not few, that's for sure. Okay, let us take our break and I'll see you in 5 minutes. All right, now the main thing we're going to talk about today is images and image data. So first thing I'm going to do is load this very popular but now very old data set called MNIST, which is these handwritten digits. And so it's basically the classification task is to take an image like this and predict what digit is it. And so this was like one of the early applications, I don't know, decades ago by now, I guess. And it was used in like the postal service to try to get postal codes or zip codes and read checks and that kind of thing. So you just want to look at an image where someone has handwritten something and just say, hey, what numbers are these? So this is a multi-class classification problem because the possible outputs are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is a 10-class classification problem, which is fine, but what's different from what we're used to is that the input is an image instead of a bunch of columns. And in fact, it's a 28 by 28 pixel image in this classic MNIST data set. Yeah, each thing is a NumPy array. Each image is 28 by 28. We have 60,000 of these images in our training set. And the question is, how can we take our 28 by 28 array, which is this image, filled with intensities, by the way, higher numbers in there are like brighter and lower numbers are darker. And so the most naive approach, if we weren't going to use anything new and we just want to use the methods we already have, like random forest or logistic regression, is to flatten the images and say, well, 28 by 28, okay, well, we have 784 features. We have the intensity of this pixel, of this pixel, of this pixel, this pixel. We have 784 pixels, and each of those can just become a feature. And so we can make each image a training example with 784 columns, where each column or feature corresponds to one of these pixels, and the number in there is the intensity. And so I can flatten them using this NumPy reshape. So I'm taking these 60,000 things and making them 784 instead of 28 by 28. I'm also dividing by 255, which is the same as min-max scaling. These pixel intensities go from 0 to 255. So instead of using scikit-learn, min-max scalar, or standard scalar, I just know that I can divide by 255 and it'll get them between 0 and 1. So I'm going to do that. And now it's like the shape that I'm used to. It's 60,000 training examples, 784 features, and it's a multi-class classification. And so I can just use whatever I want. I can use logistic regression, I can use random forest, and yeah, I don't actually have to set this. There's also a default. And I'm going to fit this. You can see I have the outputs from before. I didn't want to clear all the outputs because there's something at the end that takes 10 minutes to run. And so I wanted to leave the output there for you to see it at the end. But dang, this is taking a while. Hopefully not too long. Okay, just got some warning. So anyway, this is getting us around 93% accuracy. Oh, one thing I should say is, well, no, I'll say that later, so that's fine. Okay, yeah, so this is just a little example to say if I had an image like this, that was 2 by 2, this reshaping, this flattening is doing that. So, okay, so I got this 93% accuracy, but that's not very good for this problem, and this is a pretty easy problem. It's possible to get like super high test accuracy on this problem. although the whole like machine learning community as a whole has kind of overfit on the test set of this data set because people have just overstudied this data set. Anyways, the problem with flattening the image is we lose useful information. So when we flatten an image, the computer just sees these. It just sees these pixel intensities. It just sees like 784 features, and it lost the information that this pixel was actually next to this pixel, and this was above it, and this was over here. You're throwing away the information of what pixel is next to what other pixel, and you're only giving it this intensity. So all a decision tree could learn here is like, well, if this spot right over here is bright, then it's probably a 7. And if this spot right over here is dark, then it's probably a 0. But you don't get to use the whole like image as we see it as a human, because you're just looking at each pixel as completely separate and throwing away the information of what is next to what. And so as I'll show you later, it's just a very bad approach in general and will not get you good results. So how do we deal with this? So there's something called convolutional neural networks, which are covered in 340. And they essentially are a type of neural network that allows you to take in an image directly without flattening it and preserve that spatial information, preserve the information about what is next to what else, and you end up getting much better accuracy that way. There was a question that I loved on Piazza a while ago that was basically saying, why do we have to use ordinal encoder? Why can't we just use one-hot encoder? And then the discussion, or my answer was, well, if you had infinite amounts of data, then it could figure out, you know, a coefficient for good, a coefficient for excellent, a coefficient for average. But in the absence of infinite data, which is basically all the time, if we can give it a push, if we can give it some of our human knowledge, like, hey, there's an ordering here, bad, medium, good, excellent, then it can learn from less data. And it's kind of the same thing here. If you had infinite amounts of data and you flattened these images, it could eventually learn kind of everything it needs to know about this pixel and that pixel, but you never have infinite amounts of data. And so if you can preserve this human information, namely in this case, it is useful to know what pixels are next to what other pixels, then we should preserve that information because we will get much better results. Let me now take a look at the chat. For solving PDEs, I saw a lot of work using deep learning and it's super controversial. I was wondering, what is your comment on solving PDEs? Is this coming from LDAD and UBC, this PDE stuff that you're referring to? I don't do that kind of stuff myself, so I guess I'm not going to comment on the controversy, but I will say that our goal here is not solving PDEs, and that's outside of the scope of the tasks. Actually, no, his work was saying something else. His work was not for solving PDEs, but using ideas from that. Anyways, all that is outside of the scope of the course, so I'm not going to go into that. And I don't really know. Are TensorFlow and PyTorch the only Python packages so they can only be used in Python? Okay, great question. TensorFlow and PyTorch they live in Python by default. However, there's probably bindings for them or wrappers in other languages. I mean, I know there are. And furthermore, I think R just came out with like a PyTorch for R that's kind of pretty R native. So no, they can be used in other languages, possibly with a bit more hassle than in Python. But in any way, you can always call one language from another language if you really need to. Let's use images as data converts to tabular. Yeah, so that's not the main approach we'll be taking today. I think TensorFlow has a JavaScript version. We also have other platforms like Caffe, that's correct. Shouldn't we worry about the convergence failure or do we ignore it? Yeah, this is the question about this. Again, this is more of a 340 question. So I guess I'll just skip it. But yeah, I'll just skip it for 330 and I'll say that if you're using the default, it's probably not that horrible, but if you can always increase the max iter until the warning goes away, and that can make you feel more confident. The only disadvantage to doing that is that fit takes longer to run. So if you can increase it and make the warning go away and it's not too slow, then I would say you might as well just do that. For flattening, can we also combine a few zones of pixels? Yeah, but what convolutional neural networks do is actually something better. So we're not gonna try to salvage the flattening. What people actually do is something a bit more clever that is actually a bit related to the suggestion of using zones of pixels. Okay, keep on going. Last question. Can we parallelize the fit on deep learning? Absolutely. And that is part of why GPUs are so ingrained in this, because GPUs are kind of designed for parallel processing. So yes, there's a lot of things that can be parallelized, which is part of why GPUs can make it so fast. Okay, using pre-trained networks. So here is the main thing I want to tell you today. My main message to you today is neural networks are really cool, but also a humongous hassle. And if you've only taken this course, I do not recommend calling .fit on a neural network because it's just going to make your life too miserable because you won't have enough GPUs, you won't have enough data, you won't know how to tune the hyperparameters, and it's no fun. But as I alluded to earlier, some other nice people called fit and then posted the results online, and you can use those. So you can like go and download them from a URL and load them in. In this case, it's even more convenient because Keras TensorFlow has built right into it the ability to load someone else's fit model. So it's called pre-trained here, but pre-trained model meaning they already called fit and then they stored the results for you. The results are called weights. They're like coefficients that we saw for logistic regression. They're called weights for neural networks. Some people already stored them, and so we can just get them. And this is something that will allow you to be very powerful. It's a very low-hanging fruit for you in that you don't need to go and study that much details of neural networks, but you can immediately use them by getting some other people's pre-trained models. So here's how it works. I'm going to call this, it's loading the weights. I believe if you're calling this for the first time on your computer, it'll actually download it automatically when you call this line of code. But I've already called this line of code, so it doesn't need to re-download. And there's two things here. There's like the type of neural network and the data set. And I won't really say too much about the type of neural network, but it is useful for you to know what data set it was trained on when you take someone's pre-trained neural network. So in this case, I'm taking it from the ImageNet data set. And so you can read about the ImageNet data set, and there's 14 million images, and I think at least 1,000 classes. So someone got together this data set with a huge amount of images, and they're all labeled. Anyone can collect 14 million images, but to actually label them and say, well, this is a this, and this is that, and this is a that, can take a lot of work. And so sometimes that's actually done automatically by like looking at what images correspond to what Google searches or something, but sometimes also done by hand. It depends how trustable you need your labels to be. Long story short, this is a massive data set that you are not going to be able to collect yourself. But you want to know kind of what the images look like, because if the images look completely different from this, like if you're dealing with X-ray images, then they're not going to look like photography images. So at least you would ideally want the like modality of the images to be the same. It doesn't have to be the same camera or the same lighting or the same size, but if it is like at least vaguely matched up, that'll give you much better performance. If you're working on satellite images, try to find a pre-trained network that was pre-trained on satellite images, because if you use this, like close-up photos, and you're using satellite images, it's not going to work that well. But if you could find a vague match, then it can actually work pretty well. So here's what I did. I have this photo of my undergrad graduation photo for your amusement. I'm resizing it to 224 by 224 because that's what is expected by this image net. And so in this case, it got a bit stretched, but we need to resize our images to match the size that the pre-trained model is expecting so that we can put them into pre-trained model. And so what I can do now is I can actually, this ResNet thing is the thing I loaded up here. And I can say, hey, ResNet, you've already been trained. Someone already called fit on you. I've downloaded you. So now I can call predict. And so I can give it this image and call predict on this image. And I get, well, this is what I get. It's 99.4% proba score of bow tie, 0.2% of oboe, and 0.1% of cornet. I don't actually know what that is, but I guess that, and that's the interesting thing, right? There is a bow tie in here. And so is that right? Is it right or wrong? That's kind of a human question. So I should have said, when you look at the data set and say, is this a good pre-trained data set, you should also think about what the classes are. So you should say, are these images kind of similar enough to mine? In this case, I'm saying yes. This was a photograph that someone took. These are photographs, so I'm saying that's good enough. But I also need to know what the classes are, because it was given those 1,000 classes when it was trained. So it can only predict one of those 1,000 classes that it was trained on. Just like if our credit card fraud thing is trained on fraud and not fraud, it can't predict balloon, right? It can only predict fraud or not fraud. So likewise, this thing could only possibly predict one of the 1,000 classes that were in the training set when it was trained. And so I can't be disappointed and say, hey, it should have said Mike, because Mike was not one of the classes in the training set. And so it was never predict Mike. And so I guess whether or not we're happy with this, whether or not this is useful for what we are trying to accomplish, you need to think about that and say, well, here's the classes it was trained on. So here's the things it could predict. Is that useful for what I'm trying to accomplish? Now, the next one is a bit irrelevant these days because it's a picture of my office, which I don't go to anymore. And I maybe should have updated this for a picture of my home work environments. But I first did this a few years ago for 340, and the result was quite entertaining. So let me run the code and show you what is predicted for my office. 32.5% prison. So I thought that was pretty funny, and I didn't know if that was a sign or what, but I didn't take it as a sign. But again, it can only predict from one of the possible classes that it was given, and this is what it decided was the best. Maybe you need to renovate it. I like my office. Got my paintings, my decorative plates, my whiteboard. Anyways, moving on. So yeah, we got these predictions without calling fit ourselves. We just use it straight out of the box. So this can be useful for all kinds of things, like sentiment analysis. In the IMDb movie review thing that we did a few weeks ago, you could actually find a really fancy pre-trained model that is already trained for the purpose of saying, is this piece of text a happy or an unhappy, a positive or a negative piece of text? And you could let that loose directly on the IMDb reviews and not even call fit at all, not do any training yourself. And that could be useful. This is not relevant because I changed the order of this lecture and the next lecture. So yeah, that is kind of using a pre-trained model exactly out of the box with no modifications, which is kind of useful, but it has to now perfectly align to what you're doing. It can only, again, predict those classes. So if I wanted to make something that says Mike or not Mike, I cannot do that. But the next thing we're going to talk about is how to tweak one of these pre-trained models to use it for your problem. And that's the kind of punchline of today's lecture. That is something I expect you might find very useful out in the world. So let me first stop for questions. Looking at the chat. Okay, how big are the weights? Yeah, so actually in one of your homeworks, you're going to have to download like a gigabyte of weights for a pre-trained neural network for a language data set. So keep an eye out for that in the next couple of weeks. But it varies. It depends on the configuration of the neural network. Could be megabytes, could be gigabytes. Yeah. Okay. Okay. The model knows too much. Should we always look at the features of the pre-trained fit? Not sure what that question is asking. What are the weights? I mean, isn't the model already trained? Okay, so when you train the model, it creates the weights. Just like when you train a logistic regression, it sets those coefficients, and then you could save those coefficients and post them online and give them to someone else. For neural networks, they're called weights instead of coefficients. So when you train the neural network, it sets those weights, and then you could post them online and give them to someone else. Can't we stack these models too? Yes, we'll talk about that. Are you going to have a neural network that predicts Mike or not Mike? GB, that's so many numbers. Oh, I see. Okay, yeah, if someone has going to have a problem downloading like a gigabyte thing for the next homework, let me know and we can figure that out. Are we going to explore the size of the models and what models are better when memory is a limitation? No, we're not going to do that in this course, unfortunately. I'm confused then, what is ResNet 50? Okay, I understand. So let me scroll up. Where is it? Maybe here? Nope, too high. Ugh. Here, okay, yes, good question. So ResNet 50 is like the type of neural net. So like we have a bunch of classifiers we've seen like decision tree, logistic regression. Neural network is like a super category of a bunch of these things. And then the ResNet 50 is like the particular type of neural network. It's called the neural network architecture. I guess you could kind of say it's like we have this category of tree models, and then there's like some types like in light GBM or random forest, and this is the particular type. So this is like the particular type of neural network. And then this is the data set on which that neural network was trained. Did I hit all the questions? There was a lot of stuff in the chat. The bigger the pre-trained network, the more we'll be able to identify. Well, the bigger the network, roughly speaking, the more complex it is. And so it'll push the fundamental trade-off in that direction. But for very, very complex problems, you need very, very complex models. And so you need those big models. But roughly speaking, the bigger they are, like literally in terms of megabytes, the better training score they get and the more they might overfit. Okay, let's get to the punchline then. So what I'm going to do is introduce a new data set, which is this dog breed identification data set on Kaggle. So it basically has pictures of dogs, and the classes are the different possible breeds of dogs that you can see here. And what I'm going to do is imagine you were working on this problem of identifying dog breeds. And so you went outside, took some pictures of dogs and wrote down what the dog breed was. You wouldn't collect 1 million of these pictures. That'd be too hard. So let's assume you only had 2,000. So I'm actually going to subset this data set, and I'm only going to take 2,000 examples. If you only have 2,000 examples, and there's a lot of dog breeds here, there's 120 dog breeds. So 2,000 pictures is not really enough to solve this dog breed problem. And this is a situation you may find yourself in. Oh, it's images, so I should use neural networks, but I only collected 2,000 examples. What can I do? And so this transfer learning thing is going to come to the rescue. And so what happens here is that I have 2,000 images. Each one is 256 by 256 by 3. The 3 is for the colors. If you haven't seen that before, that's fine. And so I'm going to, again, scale these things by 255. And I'm going to just show you one of these examples. So here's one of the dogs in the data set. And your task is, given the image, can I predict which dog breed it is out of the 120 dog breeds that I'm working with? So I can do a train test split. I have 500 tests, 1,500 train. I have all these different kinds of dogs. And so if I use dummy classifier here, I get 1% accuracy. The reason we're used to dummy classifier getting like 75% accuracy. So why is dummy classifier getting 1% accuracy? Because there's so many classes. We have 120 classes, and so it's very hard to be right because there's 119 different mistakes you could make and only one right answer. And so dummy classifier is picking the most popular, which is Bernese Mountain Dog, but there's still only 20 Bernese Mountain Dogs out of 1,500 training examples. And so you're getting that 1.3% accuracy. So that is to say that before we used to think like, hey, 95% accuracy might be impressive, but here actually 30% accuracy might be really impressive because it's the more classes there are, the harder the problem is. Okay, separately from the fact there's a lot of classes, there's another issue, which is that we only have 1,500 training examples and 120 classes, which means 12.5 images per class on average. So can you imagine, like on the fraud thing, you have fraud and not fraud and 25 training examples, 12 fraud and 12 not fraud? Like you can't do anything with that. That's so few examples per class. So here, for each type of dog, we only have on average 12 images of that type of dog. And we have to do this really complicated task. That's really hard. And so here's what we're going to do. We're going to take a pre-trained model like I just talked about. In this case, this is not a ResNet, it's an Inception. It's just a different type of thing, but same basic idea. It's also trained on ImageNet. And I'm going to do this thing called include top equals false. And now is the key moment where I was telling you earlier, think about a neural net as a pipeline. Think about it as transformation after transformation after transformation, followed by some sort of logistic regression, which let's say for this case, that's basically what it is. If that's really what the neural network is doing, each of those transformations has weights in it. So when you called fit, it actually learned all those transformations and learned the ultimate classifier at the end at the same time. And so here's what I'm going to do. I'm going to say, hey, some people did a lot of work on this whole ImageNet thing. And ImageNet predicted all kinds of stuff like we saw, bow tie, prison. Those are not useful classes to me. I want to predict dog breeds. So I'm going to throw away the classifier. I'm going to take that pipeline of transformer, 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 classifier, throw away the classifier, but keep all the transformers. And then I'm going to add my own classifier on top. And that is actually going to work pretty well because a lot of the brains, I guess pun intended, of the neural network are in those transformers rather than in the ultimate classifier. So I want to keep all that. And it's going to be some black box that I don't really understand that will turn an image into a feature vector, basically, that I don't really understand. But I'm just going to train my own logistic regression on that. And then I can pick whatever classes I want. In this case, the dog breeds. And I'm going to see what I can do with that. So that's what this include top equals false. It says, I don't want your classifier. I only want your transformers in the pipeline. I don't care about your 1,000 classes that you were trained on. I want to put in my own 120 classes. And now this is just some TensorFlow stuff that we don't really need to talk about. And now here's what I'm going to do. So this thing is basic. We can think of this thing as a scikit-learn transformer. This is a thing that takes in data and transforms it to another form. And I'm not going to run this because this is one of the slow steps. But, well, it's called predict in TensorFlow Keras, but we should be thinking of this as dot transform. I'm going to call dot transform on these images of dogs, and they're going to give me a new data set whose shape is now just tabular. Now I'm going to take my 1,500 dogs. So it used to be 1,500 by 256 by 256 by 3, because each dog was a 256 by 256 image with 3 color channels. And this weird thing that I don't know, someone trained this on all their GPUs, on all their ImageNet, and posted it online. And I'm going to take it and just throw away the classifier, but keep the transformer part of the pipeline. And then I'm going to call dot transform. And now the Z thing is actually just a tabular data set with 2048 features that I don't understand, but I think they might be useful. And so, I mean, if you want, we could print it out, but it's just going to be a bunch of numbers. So there's not really a point looking at it. And I don't have column names for these columns because I don't understand what these 2048 columns are. So I can't give you names for them. But what I can do now is I can fit a logistic regression on Z train, which is my transformed images, and Y train, because this is now just tabular data like we're used to from earlier in the course. But look, I'm giving it my own, these are my own dog images. I'm transforming them with this super fancy pre-trained on image net thing, turned them into just a bunch of columns of numbers. And now I'm training where my inputs are those columns of numbers that I don't really understand. And my labels are the dog breeds, right? To remind you, these are still my labels, are still the dog breeds. And now, well, okay, this is training score, but look at this. This is amazing to me because it says all I had was 2,000 crappy training examples with 120 classes, so little data and so little data per class. And I had this ImageNet thing that someone else made, and the dog things were photographs and these were photographs, so they were kind of compatible, but what was not compatible was the classes. And so I threw away that part at the end and I said, just give me your first part of the pipeline that I don't really understand. I'm going to use that. Then I'm going to train my own thing. And 83% accuracy is really good for 120 classes, because we saw dummy classifiers only getting 1%. And you have so little data here. So this is kind of my message to you, is what I just did here is, I think, the most likely useful case for you using neural networks. Let me look at the chat. Is there a way to indicate to a particular function like predict that we want to have it run on our GPU instead of CPU? Okay, for most of these things, it'll just auto detect that you have a GPU and it'll probably just run. And yeah, maybe if it doesn't, you'll have to install some extra stuff, but it usually does. Does it mean that transform X test or X deployment takes a long time too? Awesome question. Yes, because when I'm putting this in deployment, I have to take feature extractor.predict on my deployment issue. I mean, it doesn't take that long. It took 1.5 minutes for 2,000 images. So someone can tell me what that is. Well, that's like 100 seconds for 2,000 images. So 20 images per second. So it's like 20th of a second per image, which isn't horrible, but also if it was on a GPU, it would be way faster. But yes, it would take more time than what we're used to for predicting, absolutely. Is this refitting process normal and conventional in industry? Yeah, I mean, this is not an unusual approach. And we're not, well, sure, you can call it the refitting. Sure, yes, it is standard, but if you can find like a data set that's compatible enough with yours. The question is, how do I know what type of neural network to use? Yeah, so honestly, I just tried out a few here. So I would just try out a few, would be my recommendation for this. Because I actually tried the ResNet on this and it didn't do nearly as well. And I'm sure there's a reason why, but I didn't bother to look into it. Is there a list of them somewhere? Yeah, in the Keras documentation, you can find a list of them. Okay, so if we have all black and white, would this still work? Yeah, it would still work. So actually, if you recall, that picture of me in the bow tie was black and white and it still worked. I think it basically just repeats the black and white into like the 3 color channels, red, green, and blue. And then it kind of works fine. Or so it's possible if the thing was trained on black and white and you have color, or vice versa, that can be solved. So the last thing I wanted to show you is if I compare this by just doing the flattening thing. So if I flatten these dog images, I don't use the pre-trained network. And this is the really slow thing that took an hour. I was off doing something else while this was running. If I just try to train a logistic regression directly on the flattened images, I get a 3% accuracy. So a tiny bit better than dummy classifier, but just way, 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 way worse than when we could bring in this neural network that was trained on this. Here's how I want to say it. We have a small data set here, but there is out there a massive data set that is vaguely related to what we're trying to do. And we can bring in some of those benefits of the massive data set and do much better, and then tweak it to our particular data set and use our smaller amount of data for the tweaking. Yeah, so I only have 2 minutes left, but there was some cool stuff I wanted to show you. Um, and now this is already kind of out of date. 2015 on the neural network timeline is ancient history, but nonetheless, I can still show this to you if it ever loads. There's just a lot of fun stuff with neural nets. Um, yeah, so the style transfer thing is really cool. It's like you take a photograph and you take a painting and you can transfer with the content of the photograph and the style of the painting and get this like hybrid thing that is the style of the painting and the content of the photograph. Anyway, there's a lot of really like fun, cool stuff with neural networks. And I have a bunch of links to those things over here. But I only have 1 minute left. So instead of going through all of those, well, yeah, so this was like using neural networks to like color black and white images. So they, again, trained it on a big data set so that it could kind of learn what colors things were and try to like recolor images that were old pictures that were black and white. All kinds of interesting stuff. You can click on these links if you're interested in. And then the last part of this lecture that I have moved to the end of the course is like all the bad stuff of this going horribly wrong, being, you know, racially biased and or not working as expected, being vulnerable to hacks and all kinds of things. So as awesome as this was, it's not a perfect world, and I'll talk about that more later in the course. And yeah, what did we talk about in less than 1 minute? We talked about multi-class classification. We talked about how we don't want to flatten images. We have these things called neural networks. They're a pain, but we can use pre-trained networks, which is kind of a best of both worlds thing that I hope might help you in your future careers at some point. And don't get too attached to neural networks because, well, yeah, they're kind of a pain, so just use them if there's a good reason to. Are deep fakes included in the end of the course? We could put that in, maybe send me a reminder. Anyways, I want to end on time, so I'm going to end it here. See you Thursday.